Another example of using derivatives for circuits. And this is, we're talking about an inductor. And so it says let L denote the inductance in henries of an inductor. Suppose that L is 100 millihenries, and that the current follows this function, I of t is t e to the negative 3t. It wants us to determine an expression for the voltage V of t, and what is the maximum current through the inductor for this system. So here we have our given information and our required information. And it's really not obvious where to go with this unless we know something a little bit more about circuits, which is this key expression. So our key information is that V of t is actually the inductance times the derivative of the current at a given spot. So once we understand that, then we can actually start working with things. Okay, so we can start filling in the expression. Sorry for the tilt there. Yeah, we know that, so our voltage is our inductance times the derivative of our current, and we know our current is this expression from up here. So we can just plug in our value for inductance that we have. Now taking the derivative of this expression, we haven't really talked about how to take derivatives of two things multiplied together. Turns out for that, we need the product rule. Well, what's the product? So the product rule from our differentiation rule says that if we have two functions multiplied together, then the derivative of those things multiplied together is the first times the derivative of the second plus the second times the derivative of the first. And with a little bit of simplification of not putting in all my as a function of x and that sort of thing, again, the product rule says that the derivative of two functions multiplied together is the first times the derivative of the second plus the second times the derivative of the first. So for our two functions, if we let that be f and that be g, so the first is t, the derivative of the second, so again, if we don't remember how to take the derivative of e with respect to t, of e to the something power, we just bring the coefficient of t down front and the exponent stays the same. So the derivative of this is actually times negative 3 e to the negative 3t plus, let's quarantine this off, the second, so we have e to the negative 3t times the derivative of the first. The derivative of t, hopefully we know by now, is 1. Then we should simplify that. So we can, one thing I did is I changed millihenries into henries, which will be useful because we need to get the right units in the end. And I changed our expression, and then these I just simplified, removed the negative 3 out front. This one I removed the negative 1. Another thing that would make this easier to see is if I've got negative 3, e to the negative 3t in both these terms, I can factor that out as well. And so moving that, factoring out the e to the negative 3t, I'm left with negative 3t here and plus 1 there, or I can rewrite that as 1 minus 3t inside the parentheses just to make it look a little bit better. And so there we have a equation for voltage, which is what part A asks us. So then we want to move on to part B, and part B asks us to find the maximum of the current. So what do we know about maximum? So we know that if I is at a maximum, then the derivative of I has to equal 0. And since what I just solved used the derivative of I with respect to t, I know that this part was that value. That e to the negative 3t times 1 minus I to 3t had to equal 0. Well, that only gives me two options then, right, for when it's equal to 0. Either e to the negative 3t has to equal 0, or 1 minus 3t has to equal 0. E to the negative 3t, so what value of t can I put in that gives me 0 here? Well, the other way to think about that is if I took the natural log of both sides, I would have to take natural log of 0. So there's no solution here, because I can't take the natural log of 0. So there's no value of t I can put in that would get me a value of 0. Over here, much easier. T would just be 1/3. So I get t is no 1/3, but that doesn't tell me, is that a max or a min? I don't really have a way of knowing. Well, I just wouldn't say I don't have a way of knowing. I don't know yet. What do I have to do to find out? What do I check? I check to see the second derivative. So I'd have to know, is the second derivative at that point less than 0 would be a max and greater than 0 would be a min. So to do that, next I have to find out what the second derivative of I is. So in determining the second derivative, I've got the first derivative is this. The second derivative, again, I'm going to use the product rule. So I've got my two expressions. So the first times the derivative of the second. So what's the derivative of this? That would just be -3 plus the second, which is 1 minus 3t, times the derivative of the first, which again is -3e to the -3t. So I'd have those two expressions. I would work towards simplifying them. Actually, this is a case where it does good to think about what I'm trying to solve. Remember, I'm not necessarily need to know what the second derivative is. I need to know what the second derivative is at 1/3. So at one, I could simplify this and get a much neater expression. But since I'm trying to solve it at 1/3, having that in there, I know this part's going to go to 0, which is actually going to make things a lot easier in my life. Because this is going to be e to the -1 times -3 plus, when I put 1/3 in here, this part's going to go to 0, so it doesn't really matter what the rest of that is. So at 1/3, the value is -3 over e. The main thing I need to know is that that is less than 0, so it is in fact a max. So I was right in that at t is 1/3 is a max. But what did the question ask? What is the maximum current? So the thing I haven't done yet is I need to take that and plug it back into my expression for current. And forget the tight space, but I really don't want to move on to another sheet. Should have spaced things a little bit better earlier. But yeah, so I'll plug in 1/3 into the current equation. So it's 1/3 e. Remember our current equation from way back before was t to the t times e to the -3t. So 3, put in t there, put in t there. I get 1/3 times e to the -1, which is 1 over 3e. Probably a perfectly acceptable answer for mathematics class. In engineering, we generally want it to actually be a number. So we put that in our calculator and get that it's 0.123. The units would be amperes. Or we may decide to write that as 123 milliamperes. So we know if it has that function, that's the maximum current we would get in there. Key things we learned here are about one is this expression, which helps us with inductors, and the other real thing we learned is about the product rule. We use that a couple times.